In this example, I want to demonstrate how we can solve a problem that we've tackled previously in the semester using energy methods. The problem statement is as follows. Someone standing on the edge of a cliff, 42.7 meters above the valley floor, tosses a ball straight upward with an initial velocity of 22.5 meters per second. We can neglect air resistance and can consider the ball to be leaving from the cliff itself. First question, how high above the valley floor does the ball get? Then the person does not catch the ball when it comes back down and it falls down to the valley below. Our second question, how fast is it traveling just before it hits the ground? We solved this problem previously using the kinematics equations and the acceleration due to gravity and free fall. Now let's solve it using energy methods. The first step in problem solving using energy is to draw a diagram showing the object at key points in its motion. So we'll draw our diagram here of the ball's motion. Here is the cliff going down to the valley floor. We indicate the height of the cliff, 42.7 meters. Right, 42.7 meters. The ball leaves the cliff, traveling upward at an initial speed of 22.5 meters per second. We will call that position 1. The ball travels upward and briefly stops, velocity of 0, at the peak of its motion. We'll call that position 2. The ball then comes back down before it strikes the valley floor with a speed v final, and we will refer to that as position 3. We note on our diagram that the ball reaches a maximum height, which we will call capital H. And so step 1 is complete. We've drawn a diagram showing the ball at key points in its motion. The second step is to make a decision. Like a lot of decisions we've had to make, it's an arbitrary decision, but it can be made strategically. We must decide where the ball has a potential energy of 0. The strategy here is to select the point where the object is lowest. That would be point 3 here. And call that lowest point potential energy of 0. The strategy is to avoid values of potential energy that are negative. We could solve the problem if we chose potential energy 0 to be any place, here, 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 just some random place. But this is a very strategic choice. Step 3 is at key points of the motion, write out equations for the various types of energy we're utilizing. Well, in this problem, we're going to be utilizing gravitational potential energy and kinetic energy. So we indicate what the gravitational potential energy and kinetic energy are at each of our 3 positions. Here at the top, the potential energy, here at the beginning rather, the potential energy of the ball is mgh, where h is 42.7 meters. And the initial kinetic energy is 1/2 m v naught squared. At position 2, the potential energy is mg times capital H, our maximum height, and since the ball comes to a stop, the kinetic energy is 0. Finally, here at the bottom, the potential energy is 0, and the kinetic energy is 1/2 m v final squared. So we've indicated in our diagram at each of the key points what the potential and kinetic energy values are. Step 4, we now use the principle of conservation of energy to find out what we need to find out. This is the formula for conservation of energy. The initial potential energy plus the initial kinetic energy plus the work done by non-conservative forces equals the final potential energy plus the final kinetic energy. There are, of course, other types of energy, but these are the types that concern us in this problem. For our initial position, we will select position 1, where we start. And for our final position, since we want to first figure out the maximum height, we will choose point 2 as our final position. With that in mind, our initial potential energy is the potential energy at point 1. Our initial kinetic energy is the kinetic energy at point 1. Since we are neglecting air resistance and the ball is in free fall, the work done by non-conservative forces is 0. Then, in our final position, we put the potential energy at point 2 and the kinetic energy at point 2. Now it's a matter of going back to our diagram here and filling in the blanks. The potential energy at point 1 is mg times a little h. The kinetic energy at point 1 is 1/2 mv0 squared, and that's going to be equal to the potential energy at point 2, mg times capital H, plus the kinetic energy at point 2, which is 0. One thing we note here is that there's a mass term in every part of the equation, so we can cancel out the mass, and so the mass of the ball is unimportant. This should not come as a surprise, since when we previously worked out this problem using the kinematics equations, we didn't have to worry about mass then either. Now it's time to plug in our numbers. We use 9.80 for the acceleration due to gravity, 42.7 as our initial height, plus 1/2 times the initial velocity, 22.5 meters per second squared. That's equal to 9.80 times our maximum height. Solving now for big H, that gives us a maximum height of 68.5 meters. Note that this is the maximum height above the valley floor. If we wanted to find out the maximum height above the cliff here, we would take 68.5 and subtract 42.7. So read the problem carefully and make sure you know exactly what the problem is asking of you. Our second question asks us to find this final velocity just before the ball impacts the valley floor. Well, that means obviously this is going to be our final position, but what do we choose as our initial position? We could choose either point 1 or point 2 and solve the problem perfectly fine. However, the strategic choice in this case would be to select point 1 once again to be our initial position. This is because at point 1 we have given data, a given height and a given velocity. Here at point 2 we have a calculated maximum height. So if we use point 2 as our initial position and we have made a miscalculation here, that will carry on to our answer to question 2. So the strategic choice is to utilize the given data once again. And so this left-hand side of the equation remains the same. The work done by non-conservative forces is still 0. On the right-hand side of the equation, we have the potential energy at point 3 and the kinetic energy at point 3. Once again, substituting in our equations, we get a potential energy of 0 at the bottom and a kinetic energy of 1/2 mv final squared at the bottom as well. Notice this side of the equation has not changed at all. Once again, mass cancels out. Once again, mass is not important. And so this is what we wind up with. We take 9.80 times 42.7. Once again, this side of the equation is unchanged from the previous problem, but on the right-hand side of the equation, we have 1/2 times v final squared. Multiply both sides by 2 to get rid of the 1/2. Find v final squared, and ultimately v final, we get 36.6 meters per second, to 3 significant figures for our final velocity. One thing I want to call to your attention, writing out again the working equation above, we see this. We multiply through by 2 on both sides, we get this. And rearranging the equation a bit, we get this. Why is this significant? Well, we notice that g is our acceleration, and h is our displacement. And so we notice that this is essentially kinematics equation number 3. V final squared equals V naught squared plus 2 times the acceleration times the displacement. So our energy equation has reduced to the original equation we used for kinematics. It's interesting to see the connection between the two methods.